Okay, I think I'm live, and I'm just going to do a quick audio test on my phone. Yep, audio's there. So let's keep going. It's going to be our last day in PyTorch, um, reviewing the material. I think we're only going to get about this far, um, and we won't finish the last 4 chapters for now. I might come back, um, but this is cool. So today, and let's make this definitely bigger because I'm missing my glasses, and we all know I'm basically blind. um, so, convolutional neural networks. Like yesterday, we worked on recurrent neural networks. That was mostly used for NLP. Convolutional neural networks. Oh, I forget to introduce myself. So, I'm Christina. I am a data scientist, AI strategist. Um, been doing it for over a decade. And I am currently taking 28 days to get back up to date on deep learning stuff because I really don't often get to work in it. But with LLMs and GPUs coming out, I think we're going to be moving a lot more of even some of the stuff that I would normally be doing into slightly more deep learning applications. Just not, I want to get back up on that. So I took this practical deep learning for coders course years ago, and I'm going to just go back over the content and make sure I understand the definitions, the setup, the methodologies. You're welcome to run the notebooks. You're welcome to, I would highly advise, put together projects um, based on this and just practice it without using the notebook. So I think that's the thing that a lot of um, more junior data science do is they just do the notebook, and that's not going to teach you anything. You're not going to remember it, and it's not going to look like you did anything if you put that in your portfolio, right? So redo it and go through that. We did kind of on Monday, kind of a short, brief introduction to PyTorch in general, why we chose PyTorch over TensorFlow, and that's pretty much it's pretty easy to get up and running in PyTorch because it's much more Pythonic. It is slower than TensorFlow, which is why TensorFlow is used for production. And now, actually, a lot of people are moving into JAX, which I actually have to take a look at. That's on my list of okay, do I need to learn this? Who's using JAX? Type of situation. But for a lot of what I do, which is actually, I guess I'm half and half now, getting more into productionized model development and then architecting end-to-end systems for people to use, mostly in the I don't know customer analytics space. Has been a lot of what I do. Um, so today we're in chapter 13 of the practical deep learning for coders. You can just type in GitHub Fast AI chapter 13. It should pop up, but it's in GitHub, or go to like course.fastai.com, and you can find it there. And what we're focused on today is starting at convolutional neural networks. And yesterday we were in NLP applications with recurrent neural networks. And today we're going to be focusing on convolutional ones. Now, convolutional neural networks, how are they different and what do they do? So, we did earlier in the course try to identify the number 3 and 7 in pictures with a 90 and got a 98% accuracy with Fast AI's built-in API. So they have an API that they use on top of PyTorch, which makes it faster, which covers a lot of the implementation that you'd have to do otherwise, and just does it all under the hood. So oftentimes, if you're, let's say you're doing a Kaggle competition, you want to use PyTorch, but you also want to use Fast AI on top of it so that you don't have to build all that stuff out. Not from scratch anyway. So here in this book, they're going to go through this chapter, they're going to go through some of how to build a convolutional neural network, CNN, from scratch, and the techniques to train and improve stability and learn it. So one nifty feature, which I forgot they had that oh man, it would have saved me if I remembered it, but they have this add date part in their API, and it basically takes that date column and splits it out into a bunch of columns that you can use to get information from, which is really useful. So that's a feature transformation tool function that they have in their data set. And they're going to be looking at the bulldozers data set, which is a tabular data set. And by doing that add date part and splitting out all of your times, you get a ton of feature engineering, right? Now, what are they trying to say here? Yeah, we should know what a feature is by now. So they extract the information about the image or about the edges of the image in each image and use that as the features, right? And that turns out that finding edges in an image is very common in computer vision, and that's pretty much what you do. And to do that, we do convolutions, right? So convolution requires nothing more than multiplication and addition, because again, all of what we're talking about is linear algebra applied by computers. That's why back when Andrew Ng came out with like deep learning for AI, a lot of that was how do you implement um, in NumPy matrix multiplication. And so all of it is mathematics, multiplication, addition between matrices to understand the features of that image, right? Because you convert that image into a tensor, and that tensor is a matrix of numbers that represent that image. Okay. So it applies, that convolution applies a kernel across an image, and a kernel is a little matrix. So matrix, kernel, which is a matrix in a matrix, not the movie. So such as a 3x3 matrix in the top right. So here they pull it out, they apply this to it, and they get out the number at the end of the multiplication and addition processes. So this is the convolution operator multiplies each element in the kernel by each element in the 3-block space, and the results of that multiplication added together is the convolution. So this is the tensor in a numerical representation in the code versus the image, and that's gonna be the image. It's a kernel because it's smaller than the whole 7x7 grid. This is a kernel that they took. The top edge is what they're calling it. And again, I hate all the vocabulary associated. Because that's my hardest, I think, as I've gone up in levels in, I guess, management now. The vocabulary matters because it just shortens the time to communicate. So if anyone's actually technical, you can convey that concept in a short amount of time. So it matters. And it's going to be probably the next few years the thing I work on the most. And if you will excel if you can communicate effectively in a concise manner. So they open the image, right? And this is a 3x3 pixel square. This is the original number 3 image. Now they're going to get a kernel, which is a 3x3 pixel square of this original image, and multiply each of those values by the item in their kernel. So I guess they don't call the 3x3 pixel square they get out of the image is not called the kernel. They apply the kernel they decided on, which is that 1x01 matrix to that pixel, and they call that a kernel. It's still 3x3, so I don't know. So that's what we get here. So they convert the image to a tensor, right? And then they get a 3x3 pixel square, probably top edge up here, right? Because of where these rows and columns align, and they multiply it by the kernel that they create top edge, and they get out this 0. And if they were to sum it all down, you get 0. So that is this math done for you in code. Okay. Now, I agree, this is very dull. But because if you looked at all of them, like again, they're printing out the data frame of the image that they converted into a tensor, and each of the pixels that actually have some coloration have a representative number from 0 to 255, right? So the lighter covers are not as intense, so they have a lower number, and the darker the number, the more intense that coloration, right? So it suits here. So if they're taking this top edge, there was nothing here. But if they take this numbers or these numbers and they multiply it by their kernel, something else will happen. Okay? So now they said, hey, let's top edge at the cell 5, 8, right? And so if they take 5, 8, and they go like this, they take out those numbers, 5, 8, 17, 20, right? And you multiply and you sum it down. Now we have a number. Cooking with grease, right? So this calculation returning a high number where the 3 by 3 pixel square represent the top edge, where there are low values at the top of the square and high values immediately underneath. That's because the -1 values in the kernel will have a little impact on the case, but the 1 values have a lot. So math. So if you look into the math a little bit further, right, we have if you name the pixels, they're just giving them generic names for each cell. Then this plus this is what we've got. And if we're in part of the image where A123 added to the upper 789, then the terms will cancel each other out and we'll get 0. However, if 7 is greater than 1, 8 is greater than 2, and 9 is greater than 3, we'll get bigger numbers. Well, yeah, that's just math. It just depends on the values as they do that. So this filter detects horizontal edges, more precisely edges where we go from bright parts of the image to the top to the darker. So they're just trying to capture the gradation of the image. So if they change the filter, you'll have a row of 1s at the top, and at the bottom a row of -1s, and it would detect horizontal edges that go from dark to light. So I think our current filter is, this is the current filter. So this is specifically a filter for edge detection. For detecting where the color changes in that pixel. The square, the pixel square, not the individual pixel. Okay, so now we're going to basically turn that into a function, right? So, few things. We don't need to, that's why we have variables, right? We don't need to just manually change in and out that in that function, that number that we're trying to look at, like the place where we're supposed to apply the kernel in the image, right? So we don't need to manually change that out. So they basically create variables for a row and column. And so this way, if I want row 5 -1, that's 4 because we're counting from 0 to, not, it doesn't start counting at 1, and then +2. So 5 plus 2 is 7. And it gets the high end. And from there, then you can apply it, and it applies the kernel, and it'll sum it down, and we get this. And it can only apply to complete kernels. Remember, everything has to be of the same size. So mapping a convolution kernel, we can map and apply a kernel across the grid. So basically, it just scans across like a little detector. And shows that it at how it looks, right? So you could apply it across the top here, go down 1, apply it across the next row, and get to that final row. But you can't go further down because it's not a full, like you can't pull it here, there's nothing there, according to our grid, coordinate grid. So in order to make this happen, you're going to use a nested list comprehension. If you code in Python, and actually I don't think I've mentioned this over the past few days, you need to use list comprehensions in Python. They're Python specific. They save time. If you're not using it, you're wasting time in your code. And it shows that you're not quite an intermediate Python level because you don't know how to use Python at coding. And so it's just one of those things that Interviewers will look for technical ones. If you're doing any type of coding technical interview, or if they're looking at your portfolio, they're going to look and say, okay, if they know anything. Now, sometimes you have hiring managers who aren't technical hiring managers just trying to hire a team, but any good technical is going to think through, okay, how much is this person going to cost me in server runtime, right? Because how you choose to set up your functions, the packages you should input, that increases the cost of the server and increases the cost they have to take to leadership to get money to do whatever project you want to work on. And so if they see that, they're not going to want to work with you. And that's why also one of the many reasons people no longer take entry level or interns is because they have too much to actually teach you to code, and a lot of what you learn in school is completely wrong and not up to date. So it just takes several more years to get you where you need to go, and they don't want to do that time investment. So you should really do that. A good book for this is Python Tricks or the Real Python website. Those are checked stuff by people who've coded in Python since forever. So a lot of their methods and stuff that they check are really great methods. They're not generic site like Geeks for Geeks or code.org. They're not, those are generically made sites. Anyone can put stuff on there where they've coded in that language before. It's just not, there's no base, but these guys have base. Okay. Now, the result of applying our kernel over a grid. So look at the range, the full range, the top edge tensor, and they apply that kernel all across the grid section using a nested, a nested list comprehension, because there's two, right? And then they show the image at the end. So all of the edges have been highlighted in black because that's the result of doing and applying the kernel. The bottom edges are white, opposite of the top. So now that our image contains negative numbers too, they automatically change the color. So now to get left edges, right, they switch where the positions of the ones are. So the negative ones are on the further side, one is in the middle, and you have 0, right? So they're going to now apply left edge. So now this is darker and this is lighter. So it's identified those. So a convolution is when we apply the kernel over, oh, there's a paper. Time to bookmark. I actually want to get into a lot more linear algebra stuff. If I ever have time, I'm totally self-teaching a PhD to myself. Self-taught a master's. I can self-teach a PhD. Probably get some help doing it, but I'm not great shakes at school. Okay. So basically, they are trying to demonstrate what that convolution is and show that this is the dark blue is the kernel being applied to the light blue, which is the image, and then the green is the output activation at the top. So this is the one number it calculated for this thing. This is the second number for this area, the third number for that area, the fourth number for that area, right? And that's what gives us the activation layer. So yeah, Python is slow and PyTorch speeds it up. So and there's stuff that speeds it up faster than PyTorch. So in PyTorch, the PyTorch convolution is this. So this is, remember, the fast AI import from Torch functional, right? And you can basically have your input and your weight, right? So we're going to add in the height and width of the image. Great names. So 28 by 28 is what we've been using. We'll keep using it. The height and width of our kernel, 3 by 3. Remember, we're 3 by 3 sliding grid, right? PyTorch wants a rank 4 tensor, but we're using rank 2. So the reason why is the first trick is PyTorch can apply a convolution to multiple images at the same time. That means we can call it on every item in a batch at once. Oh, time saving. The second trick is PyTorch can apply multiple kernels at the same time. So let's create the diagonal edges kernel 2 and stack all 4 the kernels into one tensor. So basically all of the diagonal edge 1, diagonal edge 2, we have all of that, and then we have the top and we have the left. And so we can apply all of these kernels at one time to get the output. So now we're going to load our data. We're going to categorize it as needed, get our labels, etc. for data loading. And normally it's on a GPU, but we can move it to a CPU. And it really depends, on what you have available and the time it'll take to do it. So we know it takes 64 images, and we're doing 28 by 28 pixels is how big the images are. So, and it can handle multicolor images too, which is great. So we don't have to think of any of the non-black pixels. So a channel is a word for the single basic color in an image. For regular full color images, there are 3 channels, which is RGB, red, green, blue. You've probably seen that before if you've done any graphic work. PyTorch represents the image as a rake 3 tensor with the dimension channels, row, columns. We'll see how to handle more than one channel later in this chapter. Okay. So we've passed the channels in, features out, rows, column, edge kernels, which are all of the kernels that we made. We just need to give it those informations in the locations. So they're going to give their edge kernel a unit axis. So I guess it can iterate through. So it's going to get the shape and unsqueeze. And so this is it, original, and this is the unsqueezed version. So it's the correct shape. So this tells it that PyTorch, the number of input channels in the kernel is 1, which we can do by inserting an axis of size 1. So the unit axis is 1. So we have 4, unit axis is 1, and they're size 3 by 3. I think that's what it's saying. So you can pass that. So now we have, they got the shape out, and I guess so this is the actual application of it. Now the batch features, this is the batch and the kernels. And so now our guess, let's see, 64 original images in the mini batch. We have 4 kernels and 26 by 76 edge maps. So we lose 1 pixel from each side because it has to be, I guess, divisible by 3. Like when we do it like the greater cross. So we lose 1 from each side. All right. So the most important trick is that we do all this work, right? GPUs. So if we don't lose those pixels on each axis, we can add paddings to it to make it correct. And then we basically add in zeros. So we can do padding. By adding it here, and then it'll go here, 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 and then to get these last 2, you add basically zeros here. And that's how it does the padding. So with that, so if we changed our inputs now, this is the original image. 1, 2, 3, 4, 5. So our input is original. And let's say you have a 4 by 4 kernel. That would be this. We'd have 2 pixels now on each side for padding that are set to 0. And so we can get this small corner, and it's going to activate here to the 6 by 6 map. all the way up. So it's going to scan across and fill in for all of those all the way to the smallest little matrix of 4. Now we can add a kernel size ks by ks. Ks has to be an odd number necessary to pad. So ks divided by 2 without remainder, I believe is what that is. And an even number for ks will require a different amount of padding. So it just depends. You need to get that math correct. So this is moving 1 pixel at a time. You can move 2 pixels at a time. So like this is 4 and then it moves over here to this one. You can do 2 at a time. All right. And that's called a stride 2 convolution. But the most common kernel size is 3 by 3. The most common padding is 1. And the reason why you'd use a stride 2 convolution are usually for decreasing the size of the outputs. Stride 1 convolutions are useful for adding layers without changing the output size. This is stride 2, basically. If you move over 2 at a time. Now, and that's, I guess, the general formula for the dimensions for this. Now, understanding convolution equations. Let's say you have a 3 by 3 image labeled as A, B, C, D, E, F, G, H. And here's the kernel weight in Greek. You apply the filter, and you get 4 new output results. So this, apply the filter, get this. Yeah, that's just a different way of explaining what we saw above. Now, this is the equation if you were to do the math by hand. Okay, so let's say A is that top right corner. It'd go alpha by A, then beta by B, Y by, I don't know what that is in Greek, but B, I don't know what that is in Greek either, E, and that would be all the way to here plus B equals this one. Lowercase b, and I'm guessing that that's something, a constant. Okay. And then you do alpha by the next one, and then alpha by D, alpha by E, all the way A, D, B, D, E, that section. And you'd go through all of it until you did it for each one. And you got your new layer. This is a term for bias. The same for each section of the image. And it's a part of the filter. So just like the weights are a part of the filter. It's a special kind of matrix multiplication. Weight matrix is just like the ones in traditional neural networks. Have the weight matrix has 2 special properties. Okay. Zeros shown in gray are untrainable. This means that they stay 0 throughout the optimization process. And that's because they weren't a part of the image, I'm guessing. Or why? Some of the weights are equal and will be trainable, changeable. They must remain equal. So they have shared weights. So let's go back. The zeros shown in gray are untrainable, meaning they stay 0 throughout the entire optimization process. Some of the weights are equal, and while they are trainable, which is changeable, they must remain equal. They are shared weights. The zeros correspond to the pixels that the filter can't touch. Each row of the weight matrix corresponds to one application of the filter. Okay, so if this is the image, and this is the filter, right, that we do it, these are gray. They can't be touched. So this is A, B, C, D, F, G. That's the full matrix. This is the bias. And then this would be the math. And once you do get rid of the zeros, you have this. And that gives you what you need. Yeah, I've seen this, but what is it called? That is a question. what is it called? Ooh, I do have my manga book of linear algebra, but I don't have my regular book of linear algebra. Okay, we'll just save it for when I pull that out and we do some review. So our first convolutional neural network. So the first thing is, just like we normally do, let's define a basic neural network. We set up the sequence, right? Linear, ReLU, linear. ReLU is removing the zeros into a continuous value. I keep forgetting what it is. I'm pretty sure that's what it is. I think I've been saying that, and I could very well still be wrong. And that's a simple neural network, right? Now, to add a convolution, we're just going to change out what looks like to be the linear parts into the convolutional parts. We're going to add our kernel size and our padding size, and we're going to do it one directional, and then we're going to do it the other way. Flip. So why is this not 28 by 28 in the input size? That's because a linear layer needs a weight in the weight matrix for each pixel, so it needs to know how many pixels are there, but convolutions applied over each pixel automatically. The weights only depend on the number of input and output channels and the kernel size that we saw in the previous session. So if we think about what the output shape is going to be, we can figure that out. So here, if we look at the output weight, 64 by 1 by 28 by 28, which is one kernel, 64 mini batch, and each of them is 28 by 28. And we need a single output activation per image, which is that layer. One way to deal with this is to use enough stride 2 convolutions such that the final layer is size 1. That is, for one stride 2 convolution, the size is to be 14 by 14. After 2, it would be 7 by 7, and then 4 by 4 and 2 by 2 in size 1. Right. 28 half is 14, 14 half is 7. 4, 2. I guess the whole factorization of it. Okay, so let's try what that means. If we create the convolution, right? You set the convolution in F stride 2 size. So this is refactoring parts of the code to decrease the errors in the architecture. Right. When we stride 2 convolution, we often increase the number of features at the same time. This is because when we decrease the number of activations in the activation map by a factor of 4, we don't want to decrease the capacity of the layer too much at a time. Channels are features. Features is never used to refer to the input data, but channels can be referred to the input data or activations inside the network. It gets so confusing. Okay, so sequential, right? So convolution, 1 by 4, which is 14 by 14, 4 by 7, 8, which is 7 by 7, 4 by 4, 2 by 2, and 1 by 1. So the sizes here increase to get the matrix here. And that shows this is the size of the activation map, this side over here, after each layer. And this will decrease the size of the activation map. And that assumes the input size is 28. So we increased it by a factor of 4. Decreasing by a factor of 4. Duh, it's going down. Okay, I think they're still answering that first question. Okay, so now the network outputs two activations which map to two possible levels in our labels. Simple convolutional batch dot shape size is 64, 2. They create their learner, and so they put a simple convolution, loss function, and they get a summary out. So they convolute at the 14 by 14, which decreases the original. They convolute again at 7 by 7 after the value. Again, they keep decreasing by a factor of 4. Which gives us a lot of parameters. Flatten removes the extra outputs, which is the same as squeeze. And then we train. And this is basically a from scratch convolutional network, which is equivalent to ResNet 18. Okay. Accesses are in HWC, batch size, tensor. So if we learn dot model sequential, four parameters, 40 parameters at the end with the weight size, 4 times 1 times 3 times 3. The bias shape, activation, so we don't have to decrease the capacity later. One bias for each channel. Sometimes the channels are called features or filters when they're not input channels. So the input is not a feature, but they are features or channel limit. The output is 64, 444, right? Because there's 4 edges, size, therefore it becomes shaped input the next layer. According to the summary, it has 296 parameters. Let's ignore the batch access to keep things simple. For each 4 by 4 is 196 locations multiplied. So let's go back to the chart. So we started here with these parameters, and we're going here with these parameters. Okay. So the next layer, 296. So after the input layer, we get 296 parameter. And they're going to ignore the batch access. And so for each of the 28 minus 8 is equal to 88 weights. So 196 times 288 minus 8. Okay, 8 is here. So 196 minus 8 is 288. That's where we get 288. I guess because when we go up this, from 1 to 4, 4 to 8, 8 to 6 is 16, 32 to 2. That is this here, the right hand. Okay. Scrolling down. (296 minus 8 equals 288). So then we take the parameters, multiply it by the weights, and we get this multiplications at that layer. The next layer, we do the same thing. 16, which would be the equivalent of the 8, and you have that, and you get this as locations. It half the grid size, and you double the number of filters from 8 to 16, resulting in no overall change in the amount of computation. Got it? Okay. Following. If we left the number of channels the same in each stride 2 layer, the amount of computation being done in that net would get less and less as it gets deeper. But we know that deeper layers have to compute semantically rich features such as eyes are first, so we wouldn't expect to do less computation. Makes sense. Okay. Receptive field. So a receptive field is the area of the image that is involved in the calculation of the layer. On the book's website, you'll find an Excel spreadsheet of convolution example XLX that shows the calculation of stride 2 convolutional layers using MNET's digit. Each layer has a single kernel and shows that we see if we click on one of the cells in the com2 section and shows the output of the second convolutional layer and traces. So this is the receptive field. Convolution filter. The cell with the green border is the cell we click on, and the blue highlighted cells are the precedents. That is the cells used to calculate the value. Got it for this cell. Precedents. These cells are corresponding 3 by 3 area of cells from the input layer on the left. The cells from the filter on the right. And now click Trace Precedents again and see that the cells are used to calculate these inputs. Filter. Okay. There. So in this example, we use 2 convolutional layers, stride 2, and they trace back to the input image. Cellular use the calculator here. Cellular is receptive field, and the input is the green activation. This is the receptive field, yeah. A large receptive field means a large amount of input image is used to calculate each activation in the activation layer. We now know that the deeper layers of a network, we have semantically rich features corresponding to each receptive field. Therefore, we'd expect that we'd need more weights for each our features to handle this increase in complexity. This is another way of saying the same thing we mentioned in the previous section. Yeah, it is. Okay. So why did we move from stride 1 convolutions with max pool to stride 2 convolutions, and why don't we use stride 1 convolutions with average pool, or do some modern nets do that? Is it just empirical, or is there some deeper reason? Has someone done the ablation studies? This depends on a lot of factors. The overall network architecture, the accelerator, TPU, etc. Some inception models use the concatenation of convolution with max average pooling, and the quality differences were marginal. Some pooling methods are more residual fringing. My original early 1989 NeuroCat paper on convolutions used stride 2 and no pooling simply because the computation was fast. The second paper used stride plus average chan worked better on zip code digits, but it could have been due to many reasons. And these are, Turing Award winners. It was mostly written by Sergey, so he might be the best person to ask. In my opinion, yours is a fair motivation of label smoothing. Interprets the passage correctly. Okay, cool stuff. So, color images. Um, it looks like they plotting it according to red, blue, and green. the convolution we did was for one filter on one channel, and we have 3 channels in an image, red, blue, and green. RBG, RGB. Okay, so we have a sliding window still. We have a lot of channels. So each channel, we need to multiply the elements by the window. And then add them together. So they basically still do the sliding window and produce a single activation layer per color. Then they add them all together. They still add the bias. And there's nothing else special about it. You can do RGB or hue saturation value, HSV, but it doesn't make much difference. So I just stick to RGB, what everyone's used to. So training stability, 10 digits. What is different? They import them all, right? And identify. So they create a baseline model. Same thing, convolution. Run the sequence. They are using more activations since we have more numbers to differentiate. They double the number of filters for each time we have a stride 2 layer. So they double the number of activations, right? So in the first layer, and then every layer thereafter will end up twice as big, yeah. But the problem is if we apply a 3 by 3 pixel kernel, that means there are a total of 3 by 3 equals 9 pixels. And that kernel being applied to each location. Previously, our first layer had 4 output filters. That meant we are 4 values being computed, right, from the 9 by 9 each location. If you double that to 8, it is a lot bigger. 9 pixels to calculate 8 numbers. That means it isn't really learning much at all. The output size is almost the same as the input. You can only create useful features if you're forced to do so. So that is the number of outputs from the operation, significantly smaller than the input. So to fix that, they use a larger kernel, okay? They're going to use a 5 by 5 kernel to increase the output, and so it gets bigger. And so now kernel size is 5, same sizes, but they're going to create 8 filters. And so instead of going from 1 to 4, we're going from 1 to 8, and we're going to increase by a factor of 8 each time we go down. And so they have a callback for that called activation stat. And it's going to record mean standard deviation hist of the activation since it's getting big. And to do that, they just call it right here. Everything else is the same as we would run it, and they're going to fit. And this is training and validation loss. Nope, it screwed up. So callback recorder, and this is the standard deviation. What was that? The mean. And what else are we looking at? Histogram of activations. Okay, this is activations. So it should be smooth. The mean and the standard deviation of a layer during trading. Activation are 0. The activations are all near 0. Yeah. That's the problem because it means we have computation model that's doing nothing at all. Yeah, it's 0. So when you see some zeros in one layer, they're therefore generally carried over to the next layer because you multiply by 0, it's 0. And you're doing multiplication. Okay, which means you get this. So in order to increase the stability, I guess we're going to be increasing batch size. Larger batches have gradients that are accurate since they calculate on more data, right? But if we use a larger batch size, we get fewer batches per epoch, which means less opportunities for the weights to update. So they're now going to drastically increase from 64 to 512, and they're going to fit. And we had about the same, but now we have here. So one cycle training. Our initial weights are not well suited to the task we're trying to solve. Therefore, it's dangerous to begin training with a high learning rate. Yeah, very well make the training diverge instantly as we've seen. We probably don't want to end training with a high learning rate either so that we don't skip over the minimum, but we want to train at a high learning rate for the rest of the training period because we'd be able to train more quickly that way. Therefore, we should change the learning rate during training from low to high. Extended schedule for learning separates two phases. One where the learning rate grows from minimum value to maximum value, which is warming up, and then one where it decreases from minimum value to annealing. And the combination approach is one cycle training. This allows us a much higher learning rate than other types of training. Benefits are you train faster or get to super convergence. Overfit less because we skip over the sharp local minimum to end up in a smoother, generalized part of loss. Is an interesting settlement. Yeah, that is not heard it. It's based on an observation that a model that generalizes well is one whose loss would not change very much. Yeah, it changed the input by a small amount. A model that trains a large learning rate for quite a while can find good loss when doing so. You must have found an area that also generalizes well because it is jumping around a lot from batch to batch. But it diverges if it jumps around a lot. So rather than seeing loss improve, you don't jump straight to a higher learning rate. Instead, you start at a low learning rate where losses do not diverge, while the optimal to gradually find smoother areas. Parameters gradually increase to higher and higher learning rates. Then once we found a smooth area of farm parameters, we want to find the very best part of that area, which means we have to bring our learning rates down. Again, this is why one cell training has a gradual learning rate ramp up and a cool down. And it is by default in the fine-tuned function in FastAI. So you get to know that it does this, but you don't necessarily have to do it yourself. And they'll go more into momentum in another chapter, and that is a technique where the optimizer takes a step not only in the direction of the gradients, but also continues to the direction of the previous steps. And cyclical momentums was introduced by a different researcher. And in that case, the momentum varies in the opposite direction of learning rate. When we are at high learning rates, we use less momentum and we use more again in the annealing phase. So that's done with fit one cycle. We do it here. There we go. If you need to view either one of these, we can here. It's going to plot the schedule. Momentum and learning rate. So learning rate went up, learning rate went down, momentum we started up and went down and went up. We can we can find the highest learning rate. We can divide by that to start, to get the starting learning rate. Get the ending learning rate, percent of batches for warm up, and then the momentum. So now if we do it, the mean, the standard deviation, and then the near zero. It was high, it dropped, it went up. I think that changed. Yes, it went down by 2 percentage points, but still. Okay, so colored in and dark colors to light colors, and is developed by fast AI in conjunction with the student. And that is a colorful dimension provides an in-depth explanation of the history and details behind the method. Basic idea is to create a histogram of the activations of the layer, which we would hope would flow a smooth pattern such as a normal distribution. So the dense colors would be here. This is a good frequency, and the red colors out here, I'm guessing. So if it's green, there's a lot of mean, and it rotates along the activation axis to 0. So they take this axis and they convert it into this at the bottom. Then they flip it on its side, and the dimension is clear if we take the log of the histogram values. The final plot for each layer is made by stacking the histogram of activations from each plot along the horizontal axis, so each vertical slice in the visualization represents the histogram of activations for a single batch. The color intensity corresponds to the height of the histogram. In other words, the number of activations in each histogram bin. So let's look at this better picture. So activations histogram is the way why the log of the function is more colorful. Okay, so this is the batch of activations. This is basically what it looks like across that distribution, right? The log is more colorful than the normal. They flip it on its axis. They flip this direction, and that makes it on a normal distribution of the histogram. Oh my goodness, all the math. And my brain is just like, this will take the log of that distribution. Okay. So why log of the function is more colorful than the function when it follows a normal distribution? Because it's taking the log, changes the Gaussian into a quadratic, which isn't as narrow. So with that in mind, let's take another look at the results. So this is bad training. Okay. It's bad training. You start with nearly all activations at 0. That's what we want to see on the far left, so it's no color. With all the dark blue. The bright yellow at the bottom represents a near 0 activation. So the activation goes from 0 to near 0. Then over the first few batches, we see number of non-zero activations increasing because it's very colorful, I'm guessing. It goes too far and it collapses back here because the dark blue returns, and the bottom becomes bright yellow again. It almost looks like training restarts from scratch. Yeah, that's true, because the distribution, it restarted over from where it was. Then we see after it starts over, again, it increases gains, and then you see the dark blue there. And then you see the spread of activations across the range. And so that means the training isn't smooth, and the cycles of exponential increases and then collapse tend to result from a lot of near 0 activations, resulting in a slow training and poor results. Got it. So to fix that, batch normalization. So they need to fix the large percentage of near zero activations to prevent it from jumping up and down. And again, more brilliant people than me created a paper, and that says training deep neural networks is complicated by the fact that the distribution of each layer's inputs changes during training as parameters of the previous layers change. This slows down the training by requiring lower learning rates and careful parameter initiation. We refer to this phenomenon as initial covariate shift, okay, and addresses the problem of normalizing layer inputs. So their solution says, making normalization a part of model architecture and performing normalization for each training mini batch. Batch normalization allows us to use higher learning rates and less careful about initiation. Paper causes great excitement. Great. So I'm guessing these are the different things they tried. This is it. This is the inception architecture that they're trying to demonstrate, and this is with other models, batch normalization with different levels. So they also added learnable parameters, meaning they updated the stochastic gradient descent, usually gamma and beta, after normalizing. That's why they have a mean variance independent from the mean and standard deviation of the previous layers. Okay, so they fit. And so now this is what they mean by smoother. So here they were near zero and they're smoothed out. They don't make the jumps up and down as you saw in the other one. And that's a smooth development of applications. Basically, it doesn't crash if we batch normalize. And basically, batch normalization adds extra randomness into the training process. And each mini batch will have a different mean instead of each other meaning batches. Therefore, the activations will be normalized by different values each time. In order for the model to make accurate predictions, it will have to learn, become more robust with the variations. And that's what adds it in. So now we see much better training and validation loss. And that brings us to that. That was the end, and there's questions at the end. Look at the files. Let me see. I think they're just going to break down ResNet. Yeah. I think the remaining chapters are just more in depth on how these work and the caveats to certain training that you probably need to know. I am going to stop here because it's Sunday and I still need to prepare for tomorrow. And we covered most of everything I wanted to cover, but just kind of the basics. Feel free to keep going through and let me know what you're working on. As always, follow me on LinkedIn or Twitter, wherever you're watching this. I have no idea. Join the newsletter if you haven't. It's on my profile somewhere. And from tomorrow, we'll start looking at CUDA programming for GPUs, because I do think that data science is shifting into two fields, and you're going to need less of one data scientist than the other. And I think the software engineering is going to become more important, because I think people are trying to implement more than they're trying to research and create new novel stuff, right? And the people who create new novel stuff typically have a lot more degrees and a lot more research. And the people who don't typically get categorized in needing more programming or more business acumen, depending on what side you fall into. And so you got to learn some new skills. And so we're going to be looking at CUDA, NVIDIA programming on GPUs tomorrow. And I look forward to having you there. Y'all have a good Sunday.